And that was a time I was locked up for 3 years abroad for something I didn't do. All right. Okay. When we look at free fall acceleration on our lovely planet, the mass and shape, irrelevant for the acceleration due to gravity, with the understanding that air resistance does kind of throw a kink in this. Near Earth, free fall acceleration is measured as the acceleration due to gravity, a sub g, or as just lowercase g if you would like. What we find is we're going to have a working value of 9.8 meters per second squared. Okay. We will never use these values, but it is nice because that really doesn't mean anything to most people. 9.8 meters per second squared says that if I drop an object, that's pretty close to what if we're just estimating? For calculation purposes, let's say it's 10, just to be nice. If I were to drop a ball without air resistance after 1 second, and its acceleration is 10 meters per second squared, how fast would it be going? After 1 second, if it accelerates at 10 meters per second every second, do you guys agree it'd be falling at 10 meters per second? Okay, after another second, what would happen? It would accelerate, so it would be going faster than 10. It'd be going 20 meters per second squared, because another 10 meters per second for that next second. After 3 seconds, 30 meters per second, and those maybe don't mean a ton to you. Other values that are worth having, and I'm going to put approximately on all of these. We will use 9.8, but there's some weird variation that does occur. Okay, if we wanted this, 22 miles per hour. After 1 second, miles per hour squared. Whoa, I got to think this out. Time. I'm not even going to include that one because I didn't do the conversions. We'll just include feet per second because that one will be more natural. Okay, 32 feet per second squared. So if I drop an object from rest, after 1 second, it's traveling at 32 feet per second. After 2 seconds, it's traveling at 64 feet per second, and 90 feet per second, and so forth and so on. Going through here, we are going to just use a working value. We will use 9.8 meters per second squared. Now, the weird part about that is there's a whole lot of big fancy physics that happens with this. We're going to talk about variations before we talk about paths. I'm not going to give you an assignment tonight, just so you know. Tomorrow, we will have a bunch of stuff to do. But let's look at a couple things. First one that I want to worry about is this is just an interesting idea. Variations in free fall. And I mentioned something at the end of class yesterday that I was supposed to remember to show at the start of class today, but I didn't. Do you recall the weird little last comment that I said, oh, we'll watch this tomorrow? It took you by surprise when I said it. We mentioned the vomit comment. Okay, now, I'll put a note here right now so I don't forget. We'll watch it tomorrow because I want to talk about this for a little while. You guys ever seen astronauts in space? Okay, not like literally, you've never been to space, I don't think. I mean, we're in space right now. Have you ever seen a video of somebody on the space station? Yeah. What's different about their lives compared to ours? They float around. Why? Love it, but it's wrong. There is gravity. There's always gravity. We'll talk about this more at length. However, there is gravity, but it's special in the way that it works, and the vomit comment is the best way to talk about that. I'm going to make a statement that I'm 100% confident of. There is nowhere in this universe, anywhere in the entire universe, on this planet, outside of our planet, anywhere, that you will not be under gravity of some sort. Now, if we imagine the Earth as a nice sphere, it's really not a perfect sphere, but I want to look at something. You don't have to draw a perfect sphere or a perfect circle, but I'm going to imagine it as a two-dimensional circle. Now, there is a little bit of, I don't want to say lying here, but we're going to make a big statement and then we're going to add some points on this. The distance between two objects influences gravity. And I'm going to say g. Lowercase g to indicate that we're talking about the acceleration due to gravity. And I didn't recall, did you guys want g or a sub g? G, okay. All right. Now, what I mean by that is on the surface of Earth, and I just want to, it's not really a brag, but I just want to show you something cool. It's not really that cool. Look at my commitment to draw on Earth. That's Alaska. Gosh, he's good. All right. Now, as we look at it, sheesh, right? All right. So as we go, at this point, we'll say point A is how we'll label this. If I said where on Earth are they, I don't care about the country. I just care about their location. Are they standing on the surface?
Yes.
What would acceleration due to gravity be here?
0.98.
Try it again. Move your decimal. Not 0.98. 9.8 meters per second squared. Okay. Now, space exists, just for the record. When you orbit in the space shuttle or the International Space Station, you are not very high up. I don't know the exact number, but it's realistically closer than this dash line is showing you. They're not very high up at all. All right. If you were to take gravity here, the reason that I want to talk about this is there is gravity in space. Space shuttles in orbit do something special, and we'll talk about that at more. But it can't be zero, because if it were zero, the moon wouldn't revolve around us. Like, there's clearly gravity there. The moon's stuck to Earth via some sort of connection. Do you think that objects up here, though, will accelerate faster or slower? Why? So there is less pull, or alternatively, the distance is larger. So if you're up here, there's a point, and I don't have this worked out as a specific distance, but maybe if you're orbiting the planet, it's 4.9 meters per second squared. If we go out further, so we're getting into deep orbit, and we just put point C all the way out here somewhere, we can keep going lower and lower and lower. There will exist a point in our orbit where gravity due to Earth's, or acceleration due to Earth's gravity, is only 2.5 meters per second squared. The distance plays a huge role. Now, quick chat, not like you guys as chat, but quick chat about why we think that there's no gravity in space due to the misleading stuff. If we launch a ball, if I were to launch, like let's say I'm going to launch a spaceship, and I launch it from the North Pole for whatever reason, and I launch it straight up, is it going to work? It's not, because that ball or that spaceship, whatever, is going to go straight up, it's going to stop, and it's going to do what? Come straight down. So this is kind of a bummer way to think about it, but let's say we're launching a missile, and I want to launch a missile from here to here. I would probably do something like this. Do you guys agree? Okay, what if I wanted to launch it to here instead? Could I launch it so that it does this instead? Like, it'll go out into space, it'll orbit, kind of. It'll take this flight path and it'll land. Now, if I launch it just a little bit faster, such that when I launch it, it hits this angle. It's going to keep falling and falling and falling, but it's falling at the exact perfect direction such that it never gets closer to the planet because we're falling around a surface. I'm just falling continuously. We'll start tomorrow with the vomit comet to really highlight this idea. Cool. What's the acceleration due to gravity on planet Earth? 9.8 what? Meters per second squared. Cool, 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 cool. Later, Raiders.